A keyboard and a display are commonly used input-output devices for microprocessor-based systems. In this section of Module 2, we will look at a peripheral IC for interfacing the 8085 microprocessor with a keyboard and a display. The 8279 is a programmable peripheral interface used to interface a matrix keyboard and a scanned LED display to the microprocessor system. The pin diagram is shown in this picture. It's a 40-pin device, out of which we can recognize some pins because they are usually found on all chips. So we have the power and ground, that's VCC and VSS, pins 40 and 20. Reset is pin number 9, clock is pin number 3. Then we have a chip select before we address the chip, that's pin number 22, and a single address line A0 with which we can address a buffer inside the chip. Then we also have the data bus signals DB0 to DB7, which connects to the microprocessor's bidirectional data bus. There is a read enable RD bar and a write enable WR bar. The rest of the pins we will learn as we continue our discussion. Before studying the architecture of the 8279 chip and its operation, we will have a look at how the matrix keyboard works with a microprocessor based system and see what are its requirements. After that, we will also take a look at the scanned multiplexed display. The circuit shows a matrix keyboard with 16 keys. If we arrange the keys in a 4x4 matrix, then we need only 8 wires from the microprocessor to do the keyboard operation. If we did not arrange it as a matrix, we would have needed 16 separate wires. So arranging it as a matrix helps us to reduce the number of wires required. The main functions of the keyboard are to detect the key that is pressed and store the value determining which key it is. The second function is called a debounce. When the key, which is a mechanical switch, is pressed, a phenomena called contact bounce happens, whereby it appears as if the switch is pressed more than once until it reaches a steady value. The same thing happens when the switch is released. It will look as if the switch is being released twice before it settles down to a steady value. So we need some circuitry to take care of switch debounce. And the last function is called a row decode, which is used to determine which key is actually pressed. It has two more functions depending on the type of keyboard it is. One is the 2-key lockout and the other one is a 2-key rollover. The 2-key lockout happens when 2 keys are pressed simultaneously, then only the first key should be read. The second one is when 2 keys are pressed simultaneously, it will save the values of both the keys in a buffer. The process by which we detect which key is pressed is somewhat complicated. First of all, we have to determine if a key is pressed or not. For that, we ground all the rows by sending zeros through the output port. Then we check the columns by reading them through the input port. If no key is pressed, all columns remain high. And we continue to repeat these two steps until the reading indicates a change. That is, some column shows a 0 value. When one of the keys is pressed, the corresponding column goes low. Then we have to identify and decode the key. Identifying the key involves another procedure. So we have to ground one row at a time. Once we determine a key has been pressed, then we should find out which key it is. For that, on the output port, we will send a 0 on each of those row wires one at a time, and then we start checking each column for 0. So once we do this, we can find out which row and which column has been shorted together and determine the code for that key. And that value is stored. So that's the procedure for the matrix keyboard operation. Now we will look at the 7-segment LED display and how to build a scanned multiplexed display using 7-segment LEDs. On the right hand side, we can see a 7-segment LED display package. So we have 7 segments numbered A, B, C, D, E, F in the clockwise direction and a segment G in the center, which can be lit as required to display the characters. All the anodes of the LEDs are connected together to have a common anode, and that is a common pin. The cathodes are separately available with separate pins for each segment A, B, C, D, E, F and G. The other diagram shows the electronic circuit, and the last one is another alternate package. The figure shows the scanned multiplexed LED display. The I/O port on the upper side would send out the required value to turn on the transistors which are used to connect the common anodes to the LEDs. So these LED displays are turned on sequentially one after the other, or they are multiplexed. The transistor is used so that it provides enough driving current for the LED segments if the IC is not able to support that much current. The individual segment pins A, B, C, D, E, F and G are connected to the other ports separately. At a time, only one LED display is turned on. From a RAM, the encoded values to display the necessary characters are sent out one by one on the data port at the bottom. So when the characters for the first LED is sent, the first LED is turned on by sending a high value to the transistor. So only the first LED is lit and it has been given the correct character code to show what is required. After a certain time, the first LED is turned off, again by turning off its transistor which connects to the anode, and the port outputs the value for the second LED, and the upper pins of the port turns on the second LED. After that, the second LED is turned off and only the third LED segment is turned on by turning on the transistor, and the required encoded signal is read from the display RAM to light the appropriate segments and display the required character in segment number 3. After some time, segment number 3 is turned off and only segment number 4 is turned on, and the appropriate code is sent to the segments for displaying the required character. And then we go back to segment number 1 again, turning off all the others. Since this is done in a sequence, in a multiplexed way, the display appears stable, showing a 4-character word to the observer. The 8279 Programmable Keyboard Display Interface IC is the hardware approach to interfacing a matrix keyboard and a multiplex display. So we saw how the matrix keyboard and the multiplex display works. Its operation can be done by software running on the microprocessor, the 8085 itself. But the disadvantage is, if the microprocessor's time is used up in sending the row checking sequence and detecting which key is pressed and also sending the scanned multiplex display outputs as required. Most of the time would be spent in doing this, and you won't have any time to do the other operation or the main function of the program which is supposed to run. So because of that, we have an IC which can offload the work from the microprocessor and do the job of managing the keyboard and the display. So it relieves the processor from these tasks. The disadvantage is, of course, the cost, and the trade-off is between the software approach is the cost versus the processor time and the software development cost. So if the processor time requirement, real-time requirement is not that high, we could get by with managing the display and the keyboard with software, or at least one of them with software. But if its speed is required, then we have to go in for a hardware approach, and the 8279 is the chip for that. We already looked at the pins that we are familiar with. Now we will look inside the chip and then find out what are the operations of the other pins based on our knowledge of how the matrix keyboard and the scanned multiplex display works. So here are the features of the 8279. It's a 40-pin IC as we saw in the pin diagram. There are two separate segments for the chip. One is for the keyboard and one is for the display. The keyboard segment can be connected to a 64 contact key matrix. That is, it has 8 rows and 8 columns. And it has an internal FIFO to store the debounced keyboard entries. The display segment can provide a 16-character scanned display interface and has a 16 by 8 display refresh RAM. The display can be set up in left entry or right entry format. That is, if we have 16 characters, we can show it as moving from the right to left or left to right. That's it. The figure shows the pin details of the 8279 grouped according to function. So the pins on the right hand side go to the I/O devices, which is the keyboard and the display, and the pins on the left hand side are the CPU interface. They go to the 8085 microprocessor. So on the left hand side we have an interrupt request going out, which indicates when the buffer inside the 8085 is full. And then we have an 8-bit bidirectional data bus which talks to the microprocessors, D0, D7 bidirectional output. And we have the read enable and the write enable and the chip select, a reset and a clock. And the signal A0 which is used to interpret the data bus word as either a control word or status or as data. The IRQ goes high whenever the data entries are stored in the FIFO, and it is used to interrupt the microprocessor. On the right hand side, if you take a look at the keyboard interface part, we have 8 lines coming in, RL0 to RL7. These are called the return lines and are connected to the 8 columns of the keyboard, plus 2 additional lines, shift and control strobe, which are status lines for the keys, which can also be stored along with the key closure. The keys are automatically debounced. The keyboard can operate in 2 modes, 2-key lockout or N-key rollover. In 2-key lockout mode, 2 keys are pressed simultaneously, only the first key is recognized. In 2-key rollover, both the keys, if they are pressed simultaneously, they are stored in the internal buffer. The keyboard section includes an 8x8 FIFO RAM, and it consists of 8 registers that can store up to 8 keyboard entries. The scan section includes a scan counter with scan lines SL0 to SL3, that's 4 lines. These 4 lines can be decoded outside to a 4 to 16 decoder to generate 16 lines for scanning. These scan lines are connected to the rows of the matrix keyboard, and the digit drivers of the multiplexed display, that is the 7-segment LED display drivers. The display section contains 8 output lines arranged in groups of 4, A0 to A3 and B0 to B3. These lines can be used in conjunction with the scan lines, the 16 scan lines coming from the decoder that's outside for a multiplexed display. That is, these 8 lines are used to drive the 7 segments of the LED. The display can be blanked by using the BD line, and the section also includes a 16 by 8 display RAM. The microprocessor unit can read or write from any of these registers. This is the architectural block diagram of the 8279. This shows how the subblocks are organized in such a way to produce the outputs that we saw in the previous diagram. The output had different sections. So here, using these subblocks and some control signals, we produce the required output for controlling the keyboard and the display devices and getting the inputs and outputs to them. So in this diagram, the upper part, there is an 8-bit internal data bus, and there are some 3 blocks above it: the data buffers, the I/O control, and the FIFO sensor RAM status. This is the part which talks to the CPU. So in the pin diagram, this was shown on the left hand side. So from the data buffers, you get the DB0 to DB7 bidirectional data output, which talks to the CPU. Then we have the read-write enables, the chip select, and the address lines, RD bar, write bar, CS bar, and AO. The clock and reset input also comes from the CPU side. And when there is some data in the FIFO sensor RAM, which is shown just below the internal data bus, the FIFO sensor RAM status bits are used to generate an IRQ. That's the yellow box on the top right. If you look below the internal data bus, on the left hand side, we will see the blocks which generate the outputs for the 7-segment matrixed display. So we have the output registers which come from a display RAM, the output data, which is the 8 bits arranged in groups of 4, A0 to A3, B0 to B3, and they are obtained from a 16 by 8 display RAM. We can address those locations and read out the code which will be sent out. On the right side, we have the blocks which talk to the matrixed keyboard. So at the bottom, you can see the dark blue box, which is the return lines, RL0 to RL7, the 8 lines for the columns of the keyboard, the shift and control inputs from the keyboard, and they go to a keyboard debounce and control, which reads the which will decode which key was pressed and then store that value in the FIFO. When the FIFO has an entry or the FIFO gets full, the keyboard debounce control will signal the status bits on top, which is the yellow box. Just to the left of the dark blue box at the bottom, which is the return, we have the scan counter, which is controlled by a timing and control block, which will generate the scan values SL0 to SL3, the 4-bit scan values which will be continuously generated as 0, 1, 2, 3, 0, 1, 2, 3, and they will be sent out onto the decode unit on the outside to generate the 16 scan lines for the matrix keyboard and the display. So in the middle, we will see some control and timing registers which are used to drive all these things as per our requirement. The I/O control at the top decides whether the CPU is reading from the data buffer or writing into the data buffer, through which it will be writing into the internal bus. So that in short is the architectural block diagram of the 8279 to perform the functions. So now we look at how to interface a keyboard with the 8279. Just the keyboard at first, and then we look at the matrix display separately, and then we will combine both of them and see how both of them can be connected with the 8279 single chip. So here we see it's an 8x8 keyboard. So we use all the return lines RL0 to RL7, and they are connected to the columns of the 8x8 matrix, and the rows are connected to 8 scan lines which come from the scan output port. So the output port needs to be only 3 because 3 lines encoded can be decoded into 8 separate lines. So that's how what's there on the right hand side. On the left hand side are the usual signals which talk to the CPU, which we have already talked about. D0 to D7 to go and write or read values, A0, then the IO write and the IO read from the 8085 are connected to the read and write bar pins here to let you know whether the processor is reading from the 8279 or writing into the 8279. Then there is a reset clock, and there is an interrupt which goes to the RST 7.5 input of the 8085, and that interrupt comes whenever there is something to be read from the keyboard buffer. The chip select is selected by means of the address lines A1 to A7. So if A1 to A6 is 0 and A7 is a 1, then we generate a signal to connect to the chip select. Yes. So that's the interface to the keyboard. This shows the format of the data word that is stored whenever a key is pressed. And that's the one that is read by the microprocessor to determine which key has been pressed. So there are bits D0 to D7. The bottom 3 bits D0, D1, D2 is the binary value of the column in which the key is pressed. That's an 8x8 matrix, so you have 3 bits to tell which column it is. And the next 3 bits D3, D4, D5 are the 3 bits which will tell which row has been pressed, and D6 and D7 are for the status of the shift and the control key. Have they also been pressed or not pressed, along with the key closure. This shows how the 8279 is interfaced with the multiplexed display. So we use the display outputs A0 to A3, B0 to B3 to control 8 LED display, and the outputs A0 to A3, B0 to B3, that's the 8 outputs, are used to drive the individual segments of the 7 segment LEDs. There are 8 of them, and then you turn them on by sending an output to the common cathode connection in this case. So we need 8 lines to select the individual LEDs, and they come from the scan lines, which are the decoded outputs of the 3 encoded scan bits. So we had 4 scan outputs coming from the 8279. 3 of them are used. They are connected to a decoder IC, which will generate 8 outputs, and those 8 outputs are individually connected to each of those transistors. So then we can turn them on in a multiplex manner one by one, and then we will be reading out the display values into the display outputs A0 to A3, B0 to B3, one after the other, and so the individual LEDs get lit with the characters we want to light. On the left hand side, it's the same interface to the microprocessor which was described earlier, and there is a chip select. Having seen the connections to the keyboard and the display, in this diagram we show the connections to the 8085. So on the left hand side, the block is the 8085 microprocessor, and it shows how the uh, connections on the right hand side of the 8279 are connected. So we already talked about how the chip select is connected, and this shows how the address lines are coming from the 8085 to the NOR gate, and the A0 is connected without inversion to form the chip select and the buffer select. Then it also shows the read and write bar enables, which are generated from the read bar, write bar, and IO bar M signal from the 8085 through a decoder to generate these two signals. The reset out is connected to reset, clock out is connected to clock, and RST 7.5 is connected to the interrupt going out of the 8279 and into the 8085. The other signals on the left hand side of the 8085 are standard signals, pin values, as we have seen. Then there is shift, control, and ground of the 8279 has been grounded over here. We have it shows the 8 LED display. We know, 4 LEDs in the display, and each LED needs 7 segments to be lit, and that's given by those display output pins 4 plus 4 as described before. Then we have the 4 scan lines coming out, and in this case they are directly connected to the matrix and the matrix keyboard and the LED display, because we have only a 4x4 matrix and 4 LEDs in this configuration. So we don't need an external decoder to generate 16 lines. So that shows this connection. This diagram shows a larger system. That is, we have 8 LEDs and 16 keyboards connected to the 8279, which is then interfaced to the 8085 microprocessor. The functioning would be similar to what was done before. This shows the arrangement by which we can have this configuration. This shows the programming for the 8279 by using the control word. So the first 3 bits are used, that is bits D7, D6 and D5. You have 3 bits, so you have 8 different combinations giving you 8 different functions, and the functions are mode set, clock, read FIFO, read display, write display, display write inhibit, clear, and end interrupts. So using these control words we can send commands to the 8279 and make it do the functions that are required. So the mode set selects the number of display positions, left or right entry, type of the keyboard scan, things like that. Clock programs the internal clock, and read FIFO selects the type of FIFO read and address of the read. Read display selects the type of display. Write display selects the type of write and address of the write. Display write inhibit allows half bytes to be blanked, and clear clears the display of the FIFO, and you can clear the interrupt signal from the IRQ. Once there is a buffer entry to be read, an interrupt request is sent to the microprocessor. Once the microprocessor has read it out, it can send this mode command of all ones to clear the interrupt. So these are the command word formats, and the word following it can specify the actual parameter in some cases. So that's all that's there in the 8279.